Hello everyone, welcome back to PID control class. Today we are going to talk about how many types can we tune PID control. And the reference is from academic paper. Let's see what it has. Mainly, there are two methods, which are sequential or closed loop method and CHR or open loop method. Okay, let's see how these two types works. The first one, the first method. Sequential or closed loop method. We will connect our system like closed loop. It will look like this. And the GPS block represents the system and KC. Once again, first connect system as a closed loop. Okay, I will zoom in for a clear picture. KC is a gain and relay in this system. After that, adjust KC until oscillation appear on our system. Okay, once again, level this Kp up until oscillation appear on our system. Oscillation is the wielding action and it has a constant period and constant amplitude. It will look like this. And then use the formula to calculate Kp, Ki, and Kd as shown in the table below. If we use only P control, the formula will look like on the first row of the table. But if we only use PI control, the formula will look like on the second row of the table. And PID control use the formula on the last row. And T variable is a period of oscillation. Also with Kc is a gain that make oscillation. And substitute T and Kc in the formula. And that's how we can find Kp, Ki, and Kd. Let's see the simulation. Okay, let's say the transfer function look like this. I will simulate the model on MATLAB. And I will use the previous window. And then change the parameter according to the example. Did you catch on? Simulate on MATLAB. First, we only have Kc, which actually is Kp. So change Ki and Kd to 0. Then we adjust Kc until oscillation appear. Okay, I will run the model to show you first. Okay, wait a second. Okay, oh, don't forget to change Kp to 1. This is the response graph change time range to 10 seconds. The yellow graph is an output, and the blue graph is an error, and the orange graph is set point. Look at the yellow graph. Response graph is a bit underdamped, and this is the normal response for closed loop. Okay, next adjust Kp until oscillation appear around 8. It's begin oscillate. See, it's begin oscillate. Although it's going to a steady state in the end. Okay, follow the value in the paper. Kp around 11.25, the oscillation will occur. Let's see how it's going to be. .25. See? Oscillation is a building action, while amplitude and period are constant. Okay, this is the oscillation. Look at the yellow graph. This is the oscillation graph. Okay, according to the paper, it's already measured about 0.84. It's about 0.84. Then use this Kc and T. Substitute in the formula. Okay, suppose that we choose PID control formula. Use this formula 0.6 Kc as a Kp and 0.6 K divided by 0.5 T as Ki and 0.6 Kc multiplied by 0.25 T as Kd. After we calculate, we will have Kp, Ki, and Kd like this. Okay, let's try it together and see how response will be. Change Kp to 6.75 and Ki to 15 and Kd to 0.76. Okay, let's see. This is the graph that delivered from sequential tuning or closed loop method. Notice that response is nearly what we want. This tuning is only a good guess method. Again, this tuning is only a good guess. We have to do a trial and error more to correct it and receive a desired response. Okay, next let's adjust PID manually for a proper value of PID. If it has an overshoot like this, what we have to do? Yes, decrease Kp. There are still some overshoot, so add more some Kd. Overshoot is lower. Ki may be too much. Look better. Okay, and add more Kd. Kd can delay the system that can decrease overshoot. And also decrease Ki, which can cause overshoot. It seems like the system we can tune our best value just like this. It might not decrease more overshoot because its property of the system cannot get rid of overshoot. It shows that sequential gives us a good gauge. When we adjust more, maybe we cannot find any better value than we have, or maybe it can be better. You have to try. Okay, let's talk about the another method, the open loop method. Tuning by open loop method is the method that we connect our system as open loop and measure response directly. This type of tuning really suits to transfer function or system which can connect system as open loop. Almost of them are first order. It is the system which is convergent only, so that it can be tuned like this. Okay, once again, this method have to connect the system as open loop and check the response which is going to be. Okay. After that, we will measure the slope around here and draw a red line through here. And we can define TU and TG. The ratio between TU and TG can tell us that if R which is a ratio between TG divided by TU. If R is more than 10, we will use only P control. Because when R is more than 10, it means that TG has a higher value than TU, so much. And also implying that the slope is very low. It means that system is very slow. If system already slow, it should not use D control. So we will use only P control. Next, if R is in this range, we will use PI control. And finally, if R is in this range, around here, we will use PID control. It indicates that the graph which in the range has a high slope. Okay, after we have TU and TG, wait, when we have TU and TG, we can use them to substitute in this formula, which are P, PI, or PID. Okay, let's try it with MATLAB. Wait, just go back a bit. In this formula, there are two types of formula we can choose, which are 20% overshoot and least overshoot. For 20% overshoot, the system works very fast, but it has overshoot about 20%. But least overshoot system may be slowed, but the overshoot will be very low. It depends on appropriation of the system. Okay, let's take a look on simulation. See on the paper, it's already delivered TU and TG. TU is around 0.2 and TG is around 1.1. So R is 5.5. And then substitute this variable in the formula. If you shoot 20% overshoot, so calculate on it. But if you shoot least overshoot, so substitute on that formula. Finally, you will have KP and KD according to this paper. First, see the simulation of 20% overshoot. I will connect system as open loop. And then change the transfer function according to a variable on paper. This is third order system. Here we have open loop system and then find a slope of the graph. See, the system is already convergent, but it might not what we want. So let's adjust it some more. We can measure all the value according to the paper in MATLAB. Okay, then let's set Kp, Ki, and Kd value, which are calculated, and see what system gonna respond. Kp shows at 20% overshoot would be 5.22. Okay, we will have all the value like on paper and then run the model. This is the response shown in the yellow line. Here, overshoot is around 20% because the graph rises up to 1.2. It's about 20%. But if we use least overshoot theory, let's see what's gonna happen. Ah, this overshoot is around 15%. And this is how we adjust PID control according to Sigrenico and CHR. But we still need to adjust manually some more to be given the best response. And the method we are going to use is trial and error. With this trial and error method, we have to know the property of PID. As I have said, P control serves to accelerate the system, make the system work faster, but it can cause overshoot, and it can reduce steady state error, but cannot get rid of it. D control serves to delay the system, make system work slower, but it also decrease overshoot and steady state error, but also increase rise time. I control will eliminate steady state error, but it can cause overshoots also. Okay, if we know like this, the first easiest thing is KP adjustment to make a fastest system as it can be. And it will look like this. It looks like a bit underdamped graph. This is the farthest point of the system. And then we will use the control to delay it down to get rid of overshoot. After that, system maybe still has some steady state error. So we will use I control to cope with it. Okay, let's see what response gonna be. This is maybe the best point of the response. Here, increase the control to 2. System was slower and overshoot was decreased. Okay, let's adjust some more. It seems like we cannot delay more than this. Okay, adjust to 15 to see if gonna take overshoot down. It cannot. Maybe this is the best point of the system. Suppose that we have changed transfer function because this function is already give us the best response. Okay, change this back to closed loop system and also change transfer function to an easier one, which is an second order. Okay, this is our response. Okay, let's increase Kp more and more until it almost reached the set point. Ah, suppose that we reach that point. If we increase more Kp, overshoot it will be exaggerated. Ah, then we will increase the control to delay the system until overshoots was eliminated. When overshoot was eliminated, you can notice that the system still has some steady state error. So increase I control to 1. Notice that the graph is sliding up. If we run time duration at 100 seconds, we will see that steady state error will be eliminated, but setting time will increase. It depends on Ki. If Ki increase, setting time will decrease. Means that response will go to steady state faster. Let's try. See? Ah, it's a bit overshoot. This is almost reached the unit step function, which is the best control system. System maybe cannot delay anymore. Maybe we have to decrease Kp because Kp is too high. Uh, Before I adjust Kp is maybe the best point of it. Okay, let's get back to it. Maybe we have to decrease Ki. See? Okay. Suppose that this is the best response we can have. Maybe one of you may adjust better than this. And this is how we do trial and error method. Trial and error is used just in case that hardware can work without damage. Otherwise, we have to use the theory which we have learned in the lecture named root locus, where we will find the best point of the system and then find Kp, Ki, and Kd. Okay, this is enough for today. The next class we will try our model with the real system and see what overshoot and oscillation gonna look like. Thank you for your attention.